Hello, everyone. Ladies and gentlemen, good afternoon. So it's my pleasure to be here. Thank you very much for this opportunity. So my name is Erick Sperandio, Nascimento. I'm Associate Professor in AI for Clean Air Systems at the University of Surrey at the People-Centered AI Institute. I'm also a member of the Global Center for Clean Air Research at the same institution. And I'm here today to talk to you about the work that we are right now developing. It's about developing a high-resolution spatial-temporal deep learning framework for air pollution forecasting to predicting its impact on human health and also finding the best scenarios for emissions reductions from anthropogenic sources for a cleaner air. It's almost an abstract, right? But it's still something that we want to depict, to highlight everything that we are doing right now, and also to bring to you this interesting proposal on how we can leverage AI to tackle sustainability challenges, mostly in this case, focus on air pollution and its impacts on human health, and how we can use AI to help us to understand how we can get the best scenarios possible to reduce anthropogenic emissions for a cleaner air. So very quick context. Of course, every one of you are much aware of this. So we have been discussed this a lot here in our air pollution strand. So, but I just want to highlight again that 99% of the world lives in areas that are exceeding WHO air quality guidelines. So these figures are from 2019. I'm just wondering how this would be nowadays, if not worse. So among this, we have around 89% of pollution-related deaths that are occurring right now in low-income and middle-income countries or regions. So we need also to take clear and quick action when we want to avoid these deaths caused by air pollution, because again, air pollution knows no boundaries. And we cannot tell, for example, people in low and middle income countries or overlooked or underrepresented regions to take the same actions as we put here, for example, in the UK or in other places or in more developed countries, for example, because it might not work, definitely. And we'd also take into account what would be feasible, what they could afford, that could enable them to take interventions, to put them in place to avoid this kind of situation. So we know that the children, the elderly, and the vulnerable groups are the ones that suffer the most when we talk about air pollution. So many of the regions lack the monitoring infrastructure needed to track or act on pollution. So we need urgent solutions so that we can not only understand these air pollution patterns, but also to predict them more accurately and also in a much faster and also sustainable way, mostly for these underrepresented areas. So this is one very interesting thing, because when we talk about this, usually we rely on computational models to do this, right? But these physical models, they are usually very expensive to run. So because of it, we are now seeing a great expense on the use and the deployment of AI solutions to be run in on par with these physical models. So for example, a good example comes from Google DeepMind. They developed, for example, for weather forecasting, for global forecasting, they developed the GraphCast model, and also the CMWF here in Europe. They also developed the AIFS model that's running, in terms of performance, on par with the IFS model, that is their numerical model, but it runs, although it's running with a very similar performance, it runs much, much faster than the numerical model. So it means that they can run right now these very powerful global weather forecasting models, but with a fraction of the time and also the computational resources to run the numerical ones using AI. So we can clearly see right now that we have the opportunity to leverage AI as well to simulate the behavior of the atmosphere. So because of it, if we take, for example, some very, very novel research that have been published recently, for example, this research that puts side by side an AI model, a deep learning model that was built using data simulated from the CIMAC model. The CIMAC model is one of the most used state-of-the-art models for photochemical, high-resolution numerical modeling of air pollution, photochemistry, and etc. So if we can see here, the time that's required to run the semantic model compared to the time that's required to run the deep learning model is really unbelievable. So you can tell the difference by looking at this kind of comparison here. So that's why many people now are investing in using and developing AI solutions that can simulate this kind of physical behavior, right? But of course, it comes with a very big challenge because we have, although we have data, we have expertise, but it's hard to build these models. So then enters our capability to develop this kind of solution. So our proposal, and the work that we are now carrying out, is about leveraging multimodal data from many different types of weather and air pollution sources. So for example, from satellite data, satellite imagery, surface weather and required stations, also emissions inventories, and many other types of data sources to ingest them into a large deep neural network, a framework that we can explore different types of novel state-of-the-art neural network architectures so that we can simulate the behavior of the air quality of the air contaminants into the atmosphere in a high resolution, spatial temporal way, but also by incorporating the physics that we already have. Instead of just relying on historical data, we can actually also incorporate the physics into these models so that we can make them not only more powerful, that can run really much faster, but also they can be more interpretable, tackling the issue of having this kind of black box models, right? And then we can actually use this to estimate and to predict the number of people that would be hospitalized by some severe air pollution scenarios. And we can do this not only for very coarse resolution, but now because AI can run much faster, we can run it for very high resolution simulations, even at an individual level. That's our main purpose here, to make it more people-centered, more sustainable as well. Then with it, we can actually also run multiple different scenarios to understand what would be the best emissions reduction scenarios that could put in place to reduce the number of people that would be affected by air pollution so that we could avoid more hospitalizations and even deaths due to air pollution. Again, because if we have this kind of tool, we can not only make it be useful for developed countries, but mostly here we are much more focused on this overlooked, underrepresented, low-resource regions that we have that are suffering right now. So for example, if you take into account the lack of data that we have, like in regions in Africa, the Middle East, and Southeast Asia, it's clear the challenge that we have, and many people are living there, that are suffering from high levels of air pollution. But if we want to make a difference, we have to have the tools, the right tools to enable the policymakers and decision makers to take the best decisions possible that are feasible and affordable to them to avoid these deaths and these hospitalizations caused by air pollution. So that's why we are now investing, and we also want to bring this to your attention because we want to do this also in a collaborative way. So the benefits are obvious. So we can optimize, this framework can be used to optimize emissions reduction scenarios from these main anthropogenic sources for a cleaner air that we can consider multiple different factors such as health impacts, technological availability, feasibility of the economical factors that we have, and social impacts as well. We can also empower researchers, modelers, and practitioners across many sectors in the society. It also can help decision makers to forecast, evaluate, and also act on air pollution impacts and risks. It can also enable large-scale, high-resolution spatial temporal operational forecasting that can also, and mostly here, include underrepresented and overlooked regions. So it also fills evidence-based policymaking, planning, and public health action that it's very much desirable nowadays, and that's why we have this our conference in place, by the way. So also it supports cleaner agendas through accessible, accurate, and scalable tools so that we can foster sustainable development for all. So to finalize this, we are now developing this proof of concept through this user-friendly web-based tool so that people without this technical background in AI computer science can run this tool in an operational basis. So because of it, it can enable actual real-time air quality forecasting with minimal computing resources. So it might catch you by surprise, but as I showed to you, these models can run much faster than any physical model that we have. So that's why we can leverage this kind of technologies for the good. It also delivers insights to all users, leading to actionable scenarios. So which kind of reductions in emissions we can put in place to minimize the impact of air pollution in people's health. This kind of question we can answer with this kind of tool. And our tool, we are developing to make it scalable across many regions in the global north and also in the global south. So for example, we have right now partners in the UK, in the US, and also in Brazil, in Africa, and also right now we are building this with colleagues from Saudi Arabia, and want to expand this to other places across the globe as well. So it can support decisions on feasibility, affordability, and health outcomes. This is it. Thank you very much. And I hope you can enjoy this and perhaps we can work together. Thank you.